So welcome everyone to this last lecture about COG, and Elias is going to tell us a little bit about where to go now. So welcome, Elias.
Thank you very much. Yes, so as David said, this last lecture, I'm trying to conclude this short lecture series that we've had. I've called it Where to Now, to sort of try to talk about what are some things that you could do after you've finished a course like this. I'm also going to talk about what I did after finishing a course like this, namely this exact course, although I took it about 10 years ago or so, so it was slightly different. But let's start by just looking at where we are right now. You have been looking at the first two volumes of the Software Foundations book, the Logical Foundations with the basics of COC and basics of logic, and the Programming Language Foundations. But there are a bunch of other volumes that you might want to have a look at as well. And that's quite a natural way to continue if you want to keep learning about COC and keep learning about what you can do with COC. So I thought I'd just give an overview of what these volumes are about. So volume 3 is called Verified Functional Algorithms, and as the name suggests, it's about functional programming, implementing functional data structures and algorithms over these and verifying them correct. And so you write COC code that you verify correct, and then you can extract that to OCaml code. So assuming that you trust that the extraction process is correctly implemented, then you get an actual compiled program that you have verified correct, or a library in case of data structures and so on. So this follows your standard algorithms course. So you have sorting, you have search trees, you have balance trees, you have priority queues, so on. And what's good to know, especially if you've been following along with this course, but maybe not taking it for credits, that this book only depends on volume 1. So if for some reason that I can't understand, you're not interested in programming language semantics and you skip that volume, you can still follow along with this book if you're more interested in the verification aspect of COC. And there are also lectures available online. So the author Andrew Appel has for a summer school called the Deep Spec Summer School of 2017. There are recorded lectures where he talks about the contents of this book. So in case you want to follow along in a similar style, albeit maybe less interactive than these lectures because they're pre-recorded, those are available. So that's a nice way to work with the book, I think. The next volume talks about property-based testing, which is a general thing that exists for many languages, but it's sort of talking about the intersection of property-based testing and theorem proving. So it's based on a library called QuickChick that was originally for Haskell, I believe, but here it's called QuickChick because of the COC meaning rooster and so on. So QuickChick is an implementation of QuickCheck, but for COC. And I won't talk a lot about it right now because we will actually look a little bit closer at this today because I think it's an interesting topic. So I'll just move on to the 5th volume, which is called Verifiable C, which uses the Princeton Verified Software Toolchain to verify C programs. So give specifications for C programs and then verifying that they are correct. So it uses, I've mentioned CompCert, the verified C compiler. So it uses that in order to, it uses the front end of CompCert in order to parse C code and then perform verification over the AST representation, basically. And this is based on, I'm going to read from the slides, a higher order impredicative concurrent separation logic and proof system, and that's the thing called verifiable C. So it's basically, maybe you know what a separation logic is, maybe you know what a higher logic is, Concurrent means that you want to be able to reason about programs that are running concurrently. And if you put all of those together, then you get verifiable C, or something like verifiable C. And actually, the final volume, currently the final volume, is called Separation Logic Foundation. So if you don't know what separation logic is, then this is an introduction where you learn separation logic by implementing it in Coq. So on a very, very high level, you've read about Hoare logic in some chapters of volume 2, which is basically pre and post condition reasoning about imperative programs. And it turns out that if you want to reason about mutable state and memory, then Hoare logic as it exists, or as it was originally specified, it doesn't really do a good job, because it's hard to say anything about aliasing. So what aliasing being when two names refer to the same memory. So what separation logic does is that it gives you a logic for reasoning about the separation of state. So the separation of memory and which parts may alias and may not alias. So comparing volume 5, and volume 6, volume 5 is more about the use of separation logic, whereas volume 6 is about implementing separation logic. So it's more theoretical, but it's a good base if what you want is to actually use separation logic to in your own research, maybe implement a tool based on separation logic. Whereas volume 5 is more about, okay, let's use cutting edge tools to do verification, mechanized verification of C programs. So that's sort of the difference between them. So these are the volumes, and I thought that we would take a quick look at, no pun intended, QuickChick. So let's do property-based testing in Coq. So what is property-based testing? Well, it provides randomized testing of properties. I should note that in contrast to everything else that we've had in the lectures, this is not something that I've used a lot myself. I've read the book and I've followed along with the exercises, but I don't have sort of real world experience with this. So I hope that I will be able to give you an overview anyway, but I might not be able to answer technical questions, but please do ask them if you have them. So what is property-based testing? Well, here I've written a function. It's a function that takes a list of natural numbers and a natural number and removes that natural number from the list. We match on it, and if the list is empty, then we return the empty list. If it's not empty, then we check if the head is equal to the thing we're supposed to remove, and then we remove it. Otherwise, we keep recursing down. And something that we might want to prove about this is a property that says that for any x and L, if you remove x from L, then x will not be in the list. So we could open up Emacs in my case and start trying to prove this. But first of all, we should stop and think, does this property hold? So it could be that there's a bug in the implementation. It could be that there's a bug in the specification. And if we start proving things, we might be wasting time, because it might turn out that we're trying to prove the wrong thing. So what QuickChick allows you to do is that after writing these two things, you can just write QuickChick remove property. And the result you will get back is that it failed. It ran 35 tests. It did 2 shrinks. We'll talk about what that is. And said it found a counterexample. So this property, when applied to the argument 2 and the list 2, 2, does not satisfy this property. Okay, so let's think about it. What's going on? if we're sending in the list 2, 2, then we get to this case. We look at the head, and we see that 2 is equal to 2. So we return the tail of the list, which is now the singleton list 2. And obviously 2 is in the singleton list 2. So if we want this property to hold, then actually we should have been recursing in this case as well, and not just returned the tail. The important thing here is that we could find this error without doing anything. We didn't have to prove anything. And just to show that it's actually doing randomized testing, let's run it here. Here I have exactly the same program and the same. So conjecture is just the same thing as axiom. It's just saying here's a property, but I'm not going to prove it just yet. So let's run QuickChick remove property. It runs for a while, and here found a different counterexample. 4 and the list 4, 4. Let's run it again. 0 and the list 0, 0. Only 4 tests this time, but it's generating random data, and it's running this thing. And if you followed along with sort of the theoretical aspects of Coq, this might surprise you, because what do you mean it's running this thing? This is in is in prop. So how can you run that to check if it holds? Typically, that's something that we need to prove. So how can we run that thing? But we'll get back to that. So property-based testing in general requires 4 things. So you need an executable property that you can test. You need generators for generating random data so that you can test if the property holds. You need a way to print this data so that you can show, if you found a counterexample, you need to present it to the user somehow. That's a small detail, but it's an important detail. And finally, if you're generating random data, it's a lot more useful the smaller the counterexample you can find. So you need shrinkers to minimize the counterexamples. So my guess in this case, so in this particular case, it was lucky, so it just did 1 shrink. Here it did 3 shrinks. So it probably had a bigger list. And after 7 tests, there was a list, and it actually failed. So it was a counterexample. And then we shrunk the list until we found a smaller list that we could actually present, because this makes it much more clear what's wrong. Luckily, the 3 last ones, for simple data, we can derive these automatically, so we don't even have to do anything. If we want better data, or if we have complicated data, then we might have to do something ourselves, but a lot of it can just be derived. And how can this be derived? Well, all of these things, except the executable properties, or to some extent executable properties as well, we'll see. All of these are based on what's called type classes, and this helps the automation of these things and the library like this. I thought I'd give a quick overview of type classes. If you programmed in Haskell, then you probably know what a type class is, but it's interesting to see how it looks, what it looks like in Coq. So a type class is a way to do ad hoc polymorphism, which is basically the same thing as overloading. So here's a class called show, and this is a typical example of a type class. It says that in the type class show, there is a single function or method, or what you want to call it, called show, that takes an A. So the class says that class A implements a type A implements the class show if there is a show function that takes an A to a string. So we can provide an instance. Here, write instance show bool, which is of type show bool. This says that this thing is now going to show us how do we implement the show function for the bool type? So in this case, we write an if statement, and if b was true, then we write true, otherwise we write false. And once we've written these two things, we can write show true, and that's going to show true. We can have another instance called show nat, which is the instance of show for the type nat. And I'm not giving you the implementation of this. I'm sure you trust me when I say that we can build a string that represents a nat. And if we have that, we can do show 42. But this is not only a matter of, hey, it's nice that we don't have to write show bool, show nat, show for every single type there is, because there's also, once we start abstracting over types and stuff, this thing turns out to be really useful. For example, let's write an instance of the option type. So the option type is either none or some x, where x has some type A. So here we've now written a weird looking thing with a backtick that says that given an A that implements the show type class, the type option A also implements the show type class. And here's how this is done. So note here that we're doing show of some option type O, and in the sum case, we're calling show on the argument x. But this show is not a recursive call to this method. That wouldn't make sense, because that would only work if x is an option type. Instead, it's one of these two, or any other instance, or I guess one of these three technically, any other instance of show. And you might have seen these braces to mean implicit arguments, and that's exactly what's going on. So we're asking Coq, please find this argument for me if I'm not providing it. And the backtick is something that was introduced when they introduced type classes in Coq, and that means that if there is a free variable inside these braces, then move that out and generalize the whole thing. So this actually implicitly has another implicit argument, which is A. But just so we don't have to write that, this is the special syntax. And writing this, we can now write show just 10 and get the string just 10. So this is already useful. It's used heavily in Haskell. You can use it in Coq as well. The TLC library that I talked about last time uses type classes a lot in order to, for example, provide unified notations. So anything that has an operation that looks like a union can use the union operation, because the union operation is going to be a notation that is implemented as a type class. But there are other interesting things that you can do since we're in a dependently typed language. We can have type classes that work over properties. I'm going to start with something that's not a type class over a property, but we're going to use that in a second. So we can say another useful thing to have is the property of decidable equality. So this is now saying we have a class called decek, decidable equality, that says that a type A implements decidable equality if any x and y of type A. So it has a function that takes an x and y of type A, and it gives us one of these things. I don't know, please tell me in the chat if you've seen this thing. It used to be part of Software Foundations, I'm pretty sure, but I'm not sure if they might have removed it for something more reflection-based. But what this is basically a disjunction. It says this is true or this is true, but it packages that into a type that has two constructors, meaning you can use it as a Boolean. So if you have a value of this type, you can deconstruct it when you're doing proofs and get, just as a disjunction, either this holds or this holds. And the you can also program with it and say, if I have something of this type, then I can do write if and this thing, and that's going to be true or false depending on if we're in the left or right thing. Let's just go back quickly. There was a comment in the chat that the example should have been show sum 10 equals. Oh, sorry. Yes, sorry. This is me being damaged by programming too much Haskell. This should, of course, have been show sum 10 to sum 10. Thank you very much, and not just. Just is what sum is called in Haskell. Sorry about that. Thanks. Okay. So we're saying that any type can implement decidable equality if it provides one of these functions. It turns out that some of these type classes, some of these instances are actually easier to implement using tactics. Let's see, I think I have that here. Here we have show. Here we have this. Here we have show option. We actually have to write generalizable variables in order to for this backtick thing to work, but then we can actually remove this thing. Right, here is this type class. And now we could have written colon equals and then write a program that actually computes one of these things. We can just write dot and then write the proof here. So I'm going to write constructor in order to apply the constructor that that wraps this type class. How this is implemented isn't important right now. And then it turns out that this thing is such a common thing to want to prove that there's actually a dedicated tactic called decide equality. So we can just use that. And now, because we want to compute with this thing, because that's the point of this thing is that it's both computable and something you can use for proofs, I'm not going to write QED, I'm going to write defined here. And now I can say compute decek 1, 2, and that gives us the right constructor. And here is the proof object. It's a quite big proof object that 1 does not in fact equal 2. So this is one of those things that we wrote, I think, that we showed that you could write by hand, I think 2 lectures ago. A more useful thing is to say compute if decek 1, 2, then true, else false. And that's going to be false, so we can actually compute with this, use this as a Boolean. Right, that's what I have here. But a more interesting type class is one that talks about decidability in general, not just about decidability of decidable equality. So you can say that any property is decidable, meaning that if we can provide something that has this type, that is the type that either P is true or P is not true. So again, this is a sum bool, which is something that we can compute with, and it's either given a property, it's going to be true or it's going to be not true. Here is an instance that shows that given a decidable equality, given that A implements decidable equality, and given two x and y's, then it's decidable whether x equals y. This looks a bit weird if you haven't seen it before. There are a lot of ticks and braces and so on. And as I told you in the first lecture, doing actual program-dependent types in Coq isn't very nice. So it's a lot nicer to just write the proof as program the instance with tactics. So let's look at that. I've given a name to this instance argument here. So first we call constructor to sort of unwrap this so that we can show this. We have a decek, so I'm going to destruct that in order to get the property that I had up here, that this thing is true, and now we have what we want, right? I think we can just do auto here even, yeah, and then defined. What's interesting now is that now we can actually do computation of properties. So here's a property 1 equals 2, and we can write compute if 1 equals 2, then true, else false. We get false. Because as we talked about 2 lectures ago, writing a proof with constructive logic is the same thing as defining an algorithm for how you derive such a proof object. And if the thing we want to prove is that something is true or not true, then we're actually providing an algorithm for checking computationally if something is true or not. So as a more interesting example, I'm not adding this to a hint database, and Coq is rightfully screaming at me for that. I hope you'll forgive me. So here we say that assuming that a type implements decidable equality, then for any x and L, it's decidable whether x is in a list L or not. The proof here, it's a proof by induction. It's not important, but you can prove this. And what's interesting now is that now I can take in 3 and the list 1, 2, 3, and I'm providing some empty arguments just to make the type checker happy. But now we can actually compute this property and see that yes, 3 is in the list 1, 2, 3, 5 is not in the list 1, 2, 3. And this shows how we could, how QuickChick is actually able to test using randomized data if a property holds or not. It's because they have to be decidable. So just by talking about type classes, we've accidentally found 2 of the ingredients needed for property-based testing. So you need an executable property, and if you have decidability, then propositions are executable as well. And you need printers, and that's just the show type class. So what are the remaining 2 ingredients then? Well, you need generators, and they might look. There's an example coming later, so I'll show you just the sort of what it is you need to provide. So there's this type G, which is the type of generators, and that's basically just a wrapper around a function that takes a natural number, which is the size of the data that you're going to produce. It takes a random seed, and then it produces one of these values. You rarely write these functions yourself. You can instead use combinators that use these under the hood to make it nicer. So there's a type class called gen with a function arbitrary that says that in order to be be able to generate random test data, you need to provide a way to give an arbitrary value. Basically, if I give you a size and a random seed, you have to provide one of these values for me. And the way this is typically done is inside of a monad. I haven't talked about monads, so if you haven't seen monads before, it's not important for the rest of this lecture, but for the people who have, this is saying that for any type G, G is a monad. No, sorry. Yes, sorry, not any type G. For exactly this type G, G is a monad, and it provides return and bind, where return just takes a value and produces a generator that only returns that value. And then you have bind that works the way bind usually works. Give me a generator of A's, a function from A to generators of B, and what you get is a generator of B. There's an example of how this looks, and it's actually easier to understand by example than by looking at this thing, especially if you haven't seen monads before. Finally, then you need shrinkers, and shrinkers are very simple. They're just the shrink type class says that given a value, you need to be able to provide a list of values, and these values should be smaller. You can trick QuickChick by actually producing larger values, and then I'm guessing that it's either it's not going to terminate or it's going to give you very bad examples. But the intention is that these lists are going to be smaller. So for example, here is a generator and a little bit later a shrinker for binary trees. I should say that these examples I've taken from the book. So I just want to be clear with my sources here. So what is this saying? It's saying we're building a generator of trees of A's. So a generator that can produce random values of trees of A's. We take as argument size, which is the maximum size of the tree that we want to generate, and we take generator G, lowercase g, which can generate A's. And then we match on the size, and we say, okay, is this size 0? Then the only tree that we can generate is a leaf, because that's the only tree that has size 0. If it's not 0, then we can provide, and this is now using one of these combinators that I mentioned. So one-off takes a list of generators and produces a generator that picks one of these at random. And the two things that we can produce, that we can generate, is either a leaf, or we can generate, you can just ignore this lift M3. This is about lifting computations in monads. If you've seen monads before, you've learned to filter them already. If you haven't seen monads before, you can just trust me when I say you can just ignore it for now. So it's saying run G, get a value, and build and run these two computations as well and get new values. Where this thing gives, this is G, so it gives you a G of A. This is just recursive calls, so it gives you generators of trees of A's, and you get a generator that produces a node of this random value and two random subtrees defined in the same way. Okay. And then finally, you can shrink data as well. So how do you shrink a tree? Well, there are several ways you can shrink a tree. So we're supposed to produce a list of, given a tree, we're supposed to provide a list of trees that are smaller. So again, we pattern match on the T. If it's a leaf, there are no smaller trees, so we just return the empty list. If we have a node in the tree, there are several ways we could shrink it. We could shrink it by returning the left subtree, that's going to be smaller. We can shrink it by providing the right subtree, that's going to be smaller. We can shrink it by shrinking the payload, the data of that node, and we use that. The function takes a shrinker of A's as argument, so it shrinks the data of the node that gives us a list, and then we map a function that just builds the same tree but with the new shrunken payload. Similarly, we can keep the tree as is, but shrink the left or right subtrees. So these together, these are 1, 2, 3, 4, 5 ways that you can shrink a tree. And the generator is what finds the counterexamples, and the shrinker is, okay, we have a counterexample, then let's generate all the smaller trees that we can and try to find the smallest possible tree that we can that is still a counterexample, and then this is what we present to the user. So that's about as much details as I was planning to give. I'll just tell you about things that is available and that you can learn if you read the book. I read the book a couple of weeks ago, and it's a nice read. There are at least for me, there were a few bugs here and there, but no showstoppers. Just some things that I couldn't get working, and I don't know if I did something wrong or if the book does something wrong. But it's a nice read anyway. So if we're generating data completely randomly, then it's going to contain a lot of repetitions. And once we've tested one randomly generated piece of data, we don't want to test that again because we know that we're going to get the same result. So if we think about this generator here, basically every second suggestion of random data is going to be just a leaf. And that's not very nice. That means that half of our generated data is just going to be leaves that we're trying over and over and over and over again. And unless that's a counterexample, that doesn't make us very happy. So just as you can use the one-off combinator to say, oh, just pick one of these at random, we can use the freak combinator. Technically, this is, I think it's a notation. There are some details that I'm leaving out, but you can think of it as a function that takes a list of not only generators, but generators with weights. So you can say with a relative probability of this thing, pick this generator. And so in this example, we could say maybe with a relative probability of 1, pick a leaf, and with a relative probability of size prime, pick this one. Then we're going to have a lot fewer leaves in our generator, which is nice, which is what we want. Another thing is that a lot of the time we are only interested in data that looks in a particular way, that has certain properties. And there is a simple way where you can use this implication operator in QuickChick to basically say this is a specification, but it's only meaningful if this precondition is holds. So what this is going to do is it's going to generate random data, check if this thing, which has to be a decidable property, check if this holds. And if it doesn't hold, we just discard the data and try again. This works, at least for some examples, but it's not very efficient, right? Because most randomly generated trees are not going to be binary search trees. And out of the few binary search trees that we happen to generate, the smaller the trees, the larger the probability is that they're actually binary search trees. So this naive solution is going to generate, it's going to skew the distribution towards smaller trees because it's a larger chance that they happen to be binary search trees. So the better way is to write better generators. So rather than writing a generator that just says, here's how you build a general binary tree, you write one that says, here is how you generate trees that are guaranteed to be binary search trees. So basically by running this generator, checking what that value is and making sure that the trees generated down here only have smaller values and the tree nodes generated here only have larger values. So wrapping up this part of the talk, the main takeaways from QuickChick, at least my main takeaways from this, is that testing helps proving. That's the first thing. And that was surprising to me. When I heard about QuickChick, I was like, what's the point of doing randomized testing when the whole idea is that we want to prove things to be correct or not? Like, if we can prove it correct, why do we need testing at all? And obviously, I was wrong because it's really nice to check if the properties that you're trying to prove hold before you actually go the distance of trying to prove them. And as you've seen, given some boilerplate that's not that hard to write once you get the hang of how to do it, then like once you have that, you can write a property and just say, please check this for me. And that's like, no one is going to write a proof that fast. No one's going to write a proof in 2.12 seconds, right? So it's really nice. But there's another takeaway, and that is that not only does testing help proving, but proving actually helps testing, because we are in a situation where we are already specifying all of these properties in a very formal way. So if we were writing just an implementation, maybe we wouldn't have like specify the property of what is this a binary search tree or not. We would just write an implementation that hopefully actually produces a binary search tree and upholds the invariance of a binary search tree. But because you're working in Coq, you've probably already specified these shapes, and you can use those to generate better input data. And I don't know, I think there are people in chat who have done property-based testing in other situations. But please tell me if there are ways to do similar things in Haskell, for example. So here's the example that I wanted to show. You say this is your basic preservation proof, right? You do has type. If E1 has type T and it's E1 steps to E2, then we want to ensure that sorry, E2 has type T. It should say E2 here. Sorry. This definition, assuming that we can show that this is decidable, then we can use this to generate well-typed expressions. Again, if we just generated random expressions, that's going to be easy, but the chances of these being well-formed is very slim. Similarly, this definition, assuming that we can write show that this is decidable, then this definition, given some input E1, we can generate expected outputs E2. And so we can generate E1s and E2s that we know are connected and we know are well typed. And so we can actually generate useful testing data and not just random testing data. I can also mention that there's also a concept of partial decidability, where maybe, for example, maybe as the steps function, if you have the while language or the imp language, I think they call it in software foundations, where you have while loops, maybe it's actually not decidable whether it terminates. Well, I guess in a small step semantics it is decidable, but there might be properties that are not decidable in general, and then you can give it a fuel argument and say, well, I can, given some fuel, I might be able to show that this thing holds or not, but I can't do it in the general case. So there are workarounds for that. And I can also mention that QuickChick, I mean, it was the PhD thesis of Leo Lam. Sorry, I'll have to cheat because I don't want to butcher his name, because I went to a really nice tutorial about this thing. Leo Lampropoulos. So this was his PhD thesis, I believe. So it's an active research project. So hopefully there will still be things happening. There's a comment as well in the chat that I don't think you'd be able to do this automatically. At least you'd have to write custom generators that do what you might be able to generate automatically from those definitions in Haskell. Yeah, that's what I think as well. So yeah, I just think QuickChick is a very nice sort of surprising thing that it works so well in Coq, and it's a nice thing to have in Coq as well. So there was a question about what does it do if it can't find a counterexample, if the thing you're proving is correct, and that's an excellent question. So let's correct this remove function here. So we should say remove x from y's, I believe, so that we keep moving. And then we have this remove property, and we do this. Let's go to QuickChick, and then it says, okay, I tried generating 10,000 tests. None of them were discarded, meaning that there were no preconditions that made them. So these were actually 10,000 tests that worked. And it stops after 10,000 tests. That's arbitrarily chosen. There are ways, I don't know that by heart, but there are ways where you can give extra arguments to QuickChick, basically saying if you wanted to start using some specific random seed, if you wanted to run more tests, and so on. So the way you typically do this randomized testing, whether you're doing fuzz testing or property-based testing, is that you will pick sort of an upper limit that's really, really large, and then you'll run it overnight or something, or over a weekend, to really weed out bugs like this. But just for finding simple mistakes, like I'm guessing 10,000 is a good number. Maybe for some applications you're going to want to increase this thing. But by default, if 10,000 tests pass, if you run 10,000 tests and you haven't found a single counterexample, that's when QuickChick gives up and basically says this might actually be true. Good question. Get started with the second part of the lecture. So this is about a project called OOlong, and there was a paper called OOlong, an extensible concurrent object calculus, that was published 6 years ago at the end of my PhD. It actually came out of simplifying a trickier project that I was working on, and this part was the part that I managed to mechanize in Coq. So as researchers, we work with understanding reality. We want to research to have a real world effect and somehow make the world a better place. Unfortunately, reality can be quite complicated, and trying to understand every single detail at the same time can make research quite unwieldy, let's say it. So instead, what we tend to do is that we build models of reality where we can abstract away some of the details that we aren't interested in, and we can make some simplifying assumptions. For example, saying that the sun is always shining and that there are always flowers and trees outside of our house. And in my line of work, the reality that we're trying to model comes in the form of programming languages, for example, Java. And the complicated details include the underlying hardware, the memory model, the memory management, like garbage collection. So typically we use models here as well. So for Java, there are a bunch of them. There's featherweight Java and classic Java and concurrent Java, lightweight Java and middleweight Java and welterweight Java. These are all different object calculi that model Java. So what's the deal here? Like, why are there so many object calculi, and why am I here trying to get you interested in yet another one? This seems like a situation where trying to squeeze another contender into the mix is just going to make things more complicated. But actually, if you look at what these object calculi, they all have slightly different levels of detail. So for example, featherweight Java, FJ, featherweight Java, it doesn't even have state. It's a completely functional subset of Java. Whereas classic and concurrent Java, they both model state. Concurrent Java has models concurrency as well. Both middleweight Java and lightweight Java are actual subsets of Java, meaning that if you have a middleweight Java program, it's also a valid Java program. Two of them model concurrency, two of them model the stack, and so on. So a common way to do research on programming languages is to start from one of these calculi and then extend it. So what I wanted to do was to find a different space in this, or a different point in this design space that wasn't focused on Java in particular. And importantly, it's an object-oriented language that makes away with class inheritance, because I think that what makes object-oriented programming interesting is subtyping, which is not necessarily the same thing as subclassing. In Java, they are intertwined, but I think you can get all the interesting stuff out of a program or of a programming language without inheritance. You can do subtyping and get all the same interesting stuff as well. Also, I wanted, because my PhD was about type systems for concurrency control, I wanted a base language where that actually had concurrency in it. And I picked some of these slides from a presentation I did about this paper. And if I was doing the full presentation, then I would now motivate why subtyping is the only important thing and so on. But we're here to learn Coq, so I'm going to skip some details and just go to the meat directly. So this is an example OOlong program. I've taken the liberty of adding ints and addition to this thing. But you have, hopefully, if you've programmed any Java or Scala or something like that, this is all readable to you. You have an interface, it's just a contract. It says these methods are available. You have a class cell that implements the counter interface by providing an integer and these two methods. And here we have a program. Note the expression-based, let-based binding rather than having statements. We create a new cell, and then we have this is a concurrency thing. It's a finish async block that runs these two blocks asynchronously. They can be arbitrarily complicated expressions. And then the finish says wait for them both to finish. And what this also does is that it takes locks. So they both operate on the same cell, but by locking, we know that they will, one of these things is going to run atomically without interruption. We don't know in which order, but it's going to add 1, it's going to add 2, it's going to, there's not going to be a data race because we put locks in this program. And then we're done, when we're done, we keep running and we call get to read the value 3 because we've added 1 plus 2. So the syntax of OOlong looks like this. So program is a list of interface definitions and class definitions and a starting expression. Interfaces are they either have method signatures, which are just a method name, a parameter and its type, and a return type, or it's an interface that extends to other interfaces. That's all you need in order to with that you can model arbitrary interfaces, as long as they're non-circular. You have classes, and a class can implement an interface. It has field definitions, it has method definitions. Fields are just names and types. Method definitions are just method signature and a function body. And here we have expressions, which is they can be values. Values are either null or a runtime construct, which is IOTA is an address on the heap. So all of these gray boxes, they are things that only appear, they never appear in source programs, but they can appear during execution. We have let bindings, you can construct objects, you can do typecasts, you can do finish async being concurrency, and you can lock things. And when you lock something, this block is actually going to be wrapped in a locked block. And that's just for bookkeeping purposes. That wouldn't exist at during runtime in implementation of this. Types are very simple. They're just classes and interfaces and unit. And we have a typing environment that both maps, when we're doing typing, we map variables to types. And when we're reasoning about the runtime state of a program, we also map heap locations to the corresponding class of that object. So let's look at the semantics then. This is static semantics. I won't go into details about everything. What's interesting from a mechanization standpoint, I think, is that it's there are quite a lot of rules. None of the rules are very complicated. Like I think almost every rule has at most 3 premises, so they're not super complicated. This one has 4, but that's just because there are many different sub-expressions. So this is the typing rules. Here we have well-formedness of a program, which is basically saying let's look at classes, for example. It says that all of the method signatures of the interface that's being implemented must have a corresponding definition in the method definitions of the class. For all fields in the field definitions, they have to be well-formed. They're well-formed if the type is well-formed. And a method definition, they also have to be well-formed, and they are well-formed if their body is well-formed when under an environment that maps this to the corresponding class and the parameter to the parameter type. So things that you sort of will make sense if you looked at semantics before, even though this is now in an object-oriented setting rather than a functional setting. During runtime, we keep track of 3 things. We keep track of a heap H, which just maps IOTAs to objects. An object is just a class, so you can do dynamic dispatch. It's a set of fields that map field names to values, and it's a lock status that is either locked or unlocked. So every object carries a lock that protects itself. In addition to the heap, we have a flat variable map. So this could have been a stack as well, but I don't keep track of stack frames. So this is just a map from variables to values. And the reason it's done like this rather than having it be substitution based like a functional language is that I wanted to reason about existing aliasing or existing references in the program, and then I don't want to look at okay what sort of pointer values or reference values exist in the running expression. I want those to be in a special place like the stack. So that's why that exists. And finally, we have a thread T, which is either a single thread E together with the lock set. That's the lock that this thread is currently holding. It can be 2 threads running in parallel, waiting to continue with this expression, or it can be an exception. And the only exception that exists is the null pointer exception, if you try to dereference something that's null. The dynamic semantics look like this. Again, I won't go through all of it, but we can sample a few of them. For example, here's select. So in order to evaluate x.f, we look up the value of x in V and get an iota. We look up the value of iota in the heap H. We get an object CFL, and in its fields F, we look up the value of F, and we get a value V, and the result is the value V. There's I think that the scariest looking rule is this one for method calls, and that's mostly because it's dealing with 2 fresh variables that it's generating, and then it's doing substitution in order to make things work, and that's it's not really that scary if you look closely. But there's an interesting rule here, which is a nice trick that if you haven't seen it before, then it's a useful thing that you can take with you. So I'm going to zoom in on that right now. You will notice that all rules do something interesting. This is a small step semantics, but I've only listed, like, all of the rules look like they do their own. They're always sort of, okay, what if we've reduced the argument of a method call to a value, or we've reduced in a let, we've reduced the thing that we're binding to a value. What happens then? And this is captured in this context rule. So there's a trick called evaluation context, which you use to abstract over congruence rules. So congruence rule is one of those boring rules that says if you have a field assignment and the right-hand side is not a value, but it can take one step, then the whole thing can take a step, ending up in the same configuration, but where we've only changed the right-hand side. And similarly, if we have a method call and the argument is not yet a value, but we can reduce the argument one step, then we can reduce the whole thing one step. And similarly for let expressions, if the thing we're binding is not yet a value, but we can step that, blah, 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 blah. It's the same thing over and over again. It takes up a lot of space in your paper. It's a lot of repetition. It's annoying when you're doing proofs and everything. So what we do instead is that we introduce a single rule that uses this external structure called an evaluation context. This is capital E, and this is saying a capital E is something that has a hole in it, and you can plug that hole with an expression. It looks like this. So the single rule that you use to replace all of them now says that if you have an expression that is the result of plugging E into this evaluation context, filling the whole of the evaluation context with an E, and this E can take a single step ending up in some configuration, then the whole thing takes a step ending up in the same configuration where we've now plugged the hole with the new E prime that we got up here. And the evaluation context can either be the right-hand, you can plug in the right-hand side of a field assignment, you can plug in the argument of a method call, you can plug in the value being bound in a let expression. In the full paper, I also have typecasts and I have this locked block. And this rule, sort of keeping all the details, is now saying that, oh, and if you have this thing captures all the congruence rules, saying, oh, and if you're not going to do anything interesting at the top level of this expression, then just do the thing in the sub expression, and then we'll plug it in there. So how would that look in Haskell then? Sorry, not in Haskell. Again, damaged by doing too much Haskell. How would that look in Coq? Well, I've experimented with a few different ones. I think the ones that work best is using functions. So one of these evaluation contexts, that's the definition E context here, it's just a function from expressions to expressions. So we can define, for example, the method call context by saying, given some variable x and some method ID m, this is just a function that takes an E and plugs that E as the argument to the method call. Obviously, there are an infinite number of methods, and we want to just say these are the ones that are correct evaluation context. So we provide an inductive type that lists all the evaluation contexts that we have. Here I've just listed one, saying that this function, CTX call of x and m, for any x and m, that is a valid context. And then in the dynamic semantics, we have that assuming CTX is an evaluation context, so one of these things, which we'll have more cases, one case for each of these. And the argument to the evaluation context can take a single step. So in the program P, it steps HV and single thread to this thing where all of these things now have been updated. And then we can step the whole thing and just plug in the new E prime into this evaluation context. And because these are functions, these are very easy to simplify and so on, because yeah, they're just functions. So we can just when we're doing proofs about this thing, we can do simple if we want to look at the inside of it, and if we don't want to, we can keep it abstract and just do proofs abstractly about the context, which is nice. This n here, you will note, does not exist in the paper version, and that's what I like to call the freshometer. So we use that to be able to generate fresh values. So we have an invariant that says that every variable that appears in V has an identifier that is strictly smaller than this n. So that's why that is there. We'll get to the differences between the paper version and the mechanized version in just a sec. I have 2 more slides with the rules, I think. So concurrency is handled by non-deterministic choice. If we have 2 threads running in parallel, we can either pick the left one or the right one and evaluate that, and that's going to update the heap and the variable map. If we have an expression which is one of these finish async things, then we're going to spawn 2 new threads and then wait with the continuation E3 afterwards. And that thing can also appear inside an evaluation context. So if you have an expression that reduces that basically spawns a new thing, and you plug that into an evaluation context, then you need to do some bookkeeping with that thing as well. And when you have 2 parallel threads and they've both been reduced to values, then you can just merge the 2 and continue with the continuation E like that. So finally, then the well-formedness rules. Let's not go through them. It's basically saying what makes a configuration well-formed. Well, the heap should be well-formed, the variables should be well-formed, the threads should be well-formed, and the threads should also be well-formed with respect to locking. So basically saying that 2 threads cannot hold the same lock, for example. And if we dig down into this thread thing, here's where we find our single-threaded typing definition. Like a thread that is not being running, that sort of when we zoom down, so we have a single thread, then this expression should have some T under the global environment. So the type soundness formulation is mostly standard. It's done by proving progress and preservation, just as in software foundations. With the exception that we now have exceptions. Again, no pun intended, I promise. So if we have a well-formed configuration, then the threads is either done, like it's reduced to a value, or it's an exception, or it has deadlocked. So there's another definition that I didn't show you that says that this is now in a state that we've defined to be okay. Like it's not unsound, it's just a state that we can't progress from because we have deadlocked. We have 2 threads that are waiting for the same, for each other's locks, for example. Or there exists another configuration such that we can take a step. Preservation is also mostly standard. It says that if we have a well-formed configuration and that configuration can step to another configuration, then there exists some environment gamma prime that subsumes the original gamma such that it types the whole thing. And this is again to do with the fact that we're keeping all the variables around. So if we had substitution, then this environment could always be empty because we would, as soon as we introduce a variable, we do substitution and then we forget about it. But now, because we're actually extending this and we're extending the heap as well, so we're keeping track of that in the environment, then we have to have a new environment. And in order to get an induction hypothesis in that is useful, we need to say that this thing is actually always going to be larger or equal to the original thing. So nothing is ever forgotten in the environment. So let's talk about the mechanization then, because that's why we're here after all. It used to be the case that you could generate these graphs automatically. Apparently, support for this was dropped in like 2020, and I didn't find an example, so I actually drew this by hand. But these are all the modules that are in the mechanization. It looks like a bit of a mess, but you can actually group these into something that makes sense. So in here we have implementation details. I used to say that any Coq project worth its salt is going to have a module that proves silly things about lists that are not in the standard library. Now I would say that any Coq project that doesn't use a reasonable standard library needs one of these. But I didn't use a reasonable standard library because I used the standard library of Coq. So I had to prove a bunch of extra things about lists. Here are things that are shared between all the properties, or sort of all the modules. So there are things like common tactics, yeah, things like this. There's a thing called meta, which is sort of how are variables implemented. Yeah, all of these are implementation details. Here we have the specification of the syntax, the dynamic semantics, the static semantics, and the well-formedness things. And then the rest of it is properties of these things and their proofs. So even the meta thing, we have proofs about these things. The dynamic semantics have properties, the types of properties, the well-formedness have properties. Locking was complicated on its own, so that got its own thing. It could have been in the dynamic prop, I guess. And then we have a module that just does the preservation proof and a module that just does the progress proof. And actually there is a final module that's just called soundness that plugs preservation and progress together. And we'll look at these in just a sec. So all of this weighs in at about 4,000 lines of code. 1,700 lines of those lines of code are specification, and a little bit more than that, 2,200 lines of code are the proofs. And about 200 lines are custom tactics that I wrote in order to make my proofs shorter. I'm also using the lib tactics that was in the Software Foundations book. I did not use a standard library because I actually just copied the file libtactics from Software Foundations and used that as is. I also, from a different course book called Certified Program Dependent Types, I took the tactics from there in order to use a tactic called crush, which is nice for proving simple things. But it doesn't, this isn't supported anymore. So yeah, I've since removed that support or removed that dependency. But again, I didn't know about TLC then, so I'm just using the tactics. In these proofs, about 800 of these lines are just about locking. So locking turns out to be extra complicated, apparently. And the mechanization, as I showed you about fresh variables and so on, so there are some uninteresting details. It's a shame we didn't have the talk about ethics, because that's an interesting discussion point, I think, David, with the the things the difference between what you present in the paper and what you present in the mechanization. I think I passed the bar, but it's something that yeah, is interesting to think about. And then there are also some other differences that are maybe a bit bigger. So for example, the heap is actually just a list, and we index that using natural numbers. In the paper version, there are these iotas that map to values. I talked about sort of these are things that can only appear during execution. that property needs to be expressed in Coq. So for example, I say that all methods are static. So when you call a method, then you get a static thing. You know that that's not going to contain in runtime machinery, but that's not in the that's not in the paper version as well. So if you compare this to some of the other mechanizations that are out there, featherweight Java, which is the functional subset, is about 2,300 lines. Well, actually, I think that this is a mechanization that's why the asterisk is there. I think it actually adds states and casts, I think, or it removes casts. There's something about casts. Lightweight Java, on the other hand, is 6,500 lines of code. And this is somewhere in between with the 4,000 lines of code. To mention that if you just take the single-threaded version, sorry, let me just pause this so I don't get notifications. But if you just take the single-threaded part of OOlong, then that's 2,600 lines of code, which is sort of similar to featherweight Java. And of course, like lines of code is a very blunt measurement. Like it's not clear what that measures, but at least it shows that it's not extremely complicated. So let's have a look at some code before I wrap up. Please let me know if there's anything that you would like to see. I've just dropped us into the, this is the, make this bigger. This is the list extras. So one thing that's really annoying before I realized that you could use a library that actually supports these sort of things is that you will be thinking about like your calculus and the way properties interact, and you will be doing a proof, and all of a sudden you need to prove something extremely obvious. For example, if you're doing find and the result is not none, then there exists an element such that find actually returns that element. And all of a sudden you need to zoom in and prove this really annoying detail. Same thing, if find returns some element, then that element is actually in the list, and so on. So bunch of boring things. There was no snock sort of adding things to the end of a list. We need to do that sometimes. So on. Actually, I could also show you. So here are just all the different files. The reason I have them in different files is that because I don't want to have to recompile 4,000 lines of code every time I change comment somewhere up there. So they're in different lists. But we do have to compile them because if we look at, let's do progress, for example, it's requiring the metaprop module, and that thing isn't compiled yet. So how do we keep track of all of these things? And it turns out that there is a nice way to do that when you've installed Coq. So you can do Coq makefile, the program, and you say take all the .v files and give me a makefile. And now we have a makefile here, and that makefile is not something that you would write by hand. It's really big. It's 1,000 lines exactly. And it does a bunch of things. For example, it lets you do, if you just do make, it runs cockdep in order to figure out what are the dependencies between the different things. And then it's going to compile all of these things in the right order, which is very nice. And so you can get a make file for free like this when you have a bigger development like this. So while this is running, let's look at syntax, for example. We have types that are classes or interfaces or unit. We have expressions, and they can be values, which are null, or one of these locations, one of these iotas. I didn't know about locally nameless that we talked the locally nameless representation that we talked about last lecture. But when looking at this, I was sort of happy that I invented something that's probably been invented before, but that uses similar ideas, although it's not nameless at all. But it sort of separates static variables and dynamic variables, and we know that. A dynamic variable are things that are going to be freshly generated, and static variables are things that are in the source code. And we know that because these are different kinds of variables, we know that they will never alias. So we don't have to worry about sort of, oh, I'm calling a method and introducing that method body. Does that method now have names that clash with things that I'm with variables that I have in scope right now? That was nice. And then the expressions are just values and variables and constructors and so on. Software Foundations uses nicer syntactic sugar in order to do these things, but yeah, I didn't get there yet. Well, I think I did. Let's look at dynamic.v. Yes. So this thing actually looks a bit nicer. Here's the the evaluation rules, and that actually uses some notation in order to say that under a program, this configuration steps to this configuration. In this particular case, this is the rule for asynchronous execution, where we take the left thread, we step that once, and then the whole thing steps. Let's find the evaluation context that we looked at. Looks unsurprisingly just as I showed you. But here are the definitions of the. Here is the evaluation context for function calls, for updates, for let expressions, for casts, for things that are locked. And here is the property that says what are valid evaluation contexts. And then we have a bunch of things, these expressions being static, finding the free variables, doing substitution, getting the locks from an expression. We have the runtime configuration where we have a dynamic variable map. And I think this partial map, I think that's in, let's see if that's in meta. Yes, so I defined that myself, including all of these classes, these type classes for decidable equality. So I wanted to know that IDs are natural numbers have decidable equality, static variables have decidable equality, and so on. And then we have maps. So basically, I'm reinventing a lot of wheels coming back to this thing. Here's the definition of something being locked. Here is a deadlock because the none of the threads can execute. Here's a deadlock because one of the threads is blocked and the other thread is done. Here is another one. Here is write locked. So this uses reader writers locked, so it's not important. But if we have a thread that trying to take the lock of some variable, and that variable maps to some location L, and that location L in the heap happens to be a locked object, and this locked object is not in the lock set of that thread, then that thread is blocked. And then the same thing can be true if this lock actually appears in an evaluation context further down. So this evaluation context saves me a lot of time, like a lot of rules that would have to be sort of be repeated for all of these things that have sub-expressions. Well, that's nice. Let's look at types. Well-formedness of types. A class type is well-formed if you can look it up in the program. Same thing for an interface. We have subsumption between two environments gamma. So if looking up one gives you exactly the same result in the other one, then the other one subsumes the first one. We have subtyping rules. We have, again, some notation for doing the type system stuff, static typing. Let's look at, maybe we can look at the soundness proof. So here is the main theorem that we're proving. So that's saying that if we have a well-formed program and we're starting from a well-formed configuration, CFG, so well-formed under some gamma, and we can take 0 or more steps to some configuration CFG prime, then let's see. There is some gamma prime that says that CFG prime is also well-formed, and this is larger or equal to the original environment gamma. And it's also the case that either the new configuration is an exception, so it's thrown an exception, or it's done, or it's deadlocked, or we can take at least one more step. And I remember this thing was very cathartic to write, because I had spent so much time proving preservation, for example. And here in this case, I can just say apply preservation. This thing that I spent so much time, and I could actually use it. And then I think in this other case, I get to apply progress somewhere. So writing this QED and the dot was, I sent a text message to my PhD advisor saying peace of mind at last, together with the definition of this thing. Yeah, let's just jump into something just to show that this is very much, okay, this wasn't actually that bad. Locking. I'm trying to find a bad example here, because this is like a lot of this is actually sort of the kind of video game proving that I've been talking about. A lot of the time I have been throwing tactics at things, and I think I should have stopped up and thought a bit more. On the other hand, like a lot of these are a lot of these proofs are complicated simply because there are so many different cases, because it's quite a large calculus. I mean, the lambda calculus is nice because it's so small, but it's also so small that it's sort of harder to map it onto something that's meaningful. But yeah, I'll go back to the thing. Let me know if there's something that you'd like to look at. But this thing is available online if you'd like to take a look. So this was, the last commit was 6 years ago, but because I wanted to look at this and I wanted to be able to run it, it turns out that this thing didn't work for recent versions of Coq. There were minor things that didn't work. Also, but this, I told you that I was using the crush tactic, and that had not been maintained, so I could not get that working for the latest version of Coq. Maybe someone has made it has made it work, but I couldn't do it. So what I did was actually 2 days ago, I made this thing work for a latest version of Coq. I've removed the libtactics file and instead depend on TLC as an external library, as one should instead, and then remove the crush tactic and use TLC. So there was some, I had to go through these 4,000 lines of code to fix some proofs that were broken. Also, back in my day, it was perfectly fine to add things to add hints without specifying a database, but now that's frowned upon, so I fixed that as well. And there's obviously, I could probably get rid of list extras and rely on TLC. Maybe we could use the freshness tactics from TLC as well to remove some of that machinery. I don't know if that is something that I'll ever get around to doing, but at least the pull request is up there so that you can look at a version that actually runs. And obviously this is open source, so if anyone wants to do this work for me, then by all means, I'm not going to stop you. There was a question here. Did you use your formalization to type check example programs? I don't know. I think I did. I know that I've done that for some mechanized language, but there is no example file here. So it seems like if I did, then this is not included here. So that's something that you can definitely do, but sort of type checking things by hand, even though it's nicer in Theorem Prover, is still quite annoying. Is it a good idea? I think it could be a good idea. It depends on what kind of type system you're using. I think in this case, it's like I'm not doing any weird things. So I'm like, it's probably a good idea just for sanity checking, but let's say I was doing something more interesting. Let's say I was mechanizing parts of Rust or some similar type system or language that has, where I'm actually claiming, look, I can write these sort of languages and the type checker is going to give me these properties. Then I think it's definitely a good idea to check that your mechanization actually supports the languages that you or support the programs that you claim that you support. So I think that it's a very good idea. Possibly a related question. Let's see here. Do you think that QuickChick would have been useful to use if it would have been available at that time? If yes, in what way? It would very much have been useful. And if I started a big project like this, then I would definitely jump through the hoops of writing generators and so on, because there were so many things that, like, small errors that I made, or small sort of discrepancies, small details that I got wrong, because again, sort of 1,200 lines of specifications, 16 maybe. So with QuickChick, I would have been able to find those a lot quicker, rather than spending a day trying to prove something and then realizing, oh, this thing doesn't actually hold, like you can't prove it. So I think QuickChick would have been very useful. I assume that the machinery that makes, for example, properties decidable in QuickChick would also have been useful for the previous question, because then I would have gotten a decidable instance for type checking, and then I could have possibly sort of derived a very inefficient but still working type checker for programs, so that I could actually type check my programs programmatically, but without having to step through the proof of doing it, but actually letting the decidable version of the type checking property do that for me. I don't know whether this works or not, but I would guess that something like that would work. So the world is turning into a better place, because there are now better tools than there was 6 years ago. So to sort of wrap up this lecture and basically wrap up the whole lecture series, so there sort of my first real Coq project, it was a bit rough around the edges. Like there are a lot of invented wheels. There are many things that we do differently today. So for example, like there's a list extras. I have a type for maps. I have a type for environments. I have a sort of type for variables, freshness, and so on. I think this is very common for junior developers, and that's true for junior proof developers as well. But if I were to do the same thing again, then I would try to reuse existing things. For example, I mean, you know by now that I like the TLC library, but use some existing library instead. I mean, to an extent, I was doing that with the tactics because I realized that the tactics were helping me, but I didn't think as far as seeing if some of these structures and things I wanted to do with the semantics was available. I think I would also try to be smarter rather than faster. Again, with the video game proving, because it's so addictive to get to type that QED dot, being able to think. I try nowadays to think more about what I'm proving and how to prove it, and maybe stop earlier than when I'm at my 5th nested bullet to think of, I should probably prove a lemma in order to make this nicer. I would rather have 100 lemmas that are all has a nesting depth of at most 2 than 10 theorems that all have a nesting depth of 5, because yeah, it's hard to maintain, it's hard to work with. But I think the most important thing I learned was sort of this idea of proof engineering that I mentioned in the very first lecture. Like, how do you handle this big proof? Like, it's very quickly. I also had an older computer, so sort of compile, type checking everything took a longer time. So sort of thinking about how do you modularize these things? How do you manage dependencies? How do you compile these things, and so on? And sort of doing a larger project like this was useful for that. So I can only say, sort of, if you're doing some sort of formal development, then try doing it in Coq the next time. You learn a lot, and if you get there in the end, then you have like you have a really solid artifact that you can use for your paper. Like you have something that you can really trust. And because we've had other people lecturing here, obviously there are other proof assistants that are also really nice. I watched Magnus Merien's lecture, the recorded lecture, and yeah, if I had the time, I would love to learn some Hol 4 and some Agda as well. But so I think what I want you to take away is not necessarily that you should use Coq, but you should sort of using proof assistance. I think that is very much the future of formal work. So with that said, good luck in the future, and thank you for listening to and attending these lectures.
Very good. Thank you. Thanks a lot, Elias, for all your hard work of presenting this over during the spring. And with that, I think we should end this lecture, and then the rest of us will meet at the next seminar, the last seminar, where we'll both discuss ethics and also have the presentations for the Coq proofs. All right. Thank you,
Great.
everyone. Take care.
Thanks. See you guys.